Hello, my name is Hunter Gabbard, and I'm a physics and astronomy PhD student at the University of Glasgow. And today I'm going to present some work on behalf of other colleagues in the School of Physics and Astronomy and the School of Computing Science, entitled Bayesian parameter estimation using conditional variational autoencoders for gravitational wave astronomy. And just a brief overview of what I'll be talking about for the next few minutes, just kind of an introduction to the poster. I'll kind of describe what gravitational waves are, which is a large part of this work. I'll give some motivation behind why we're doing this work, what we did, and of course, given some of the results, what do we plan to do next? So gravitational waves were actually predicted by Einstein over 100 years ago in 1916 in his very famous theory of general relativity. And essentially what they are ripples in the very fabric of space and time. Are incredibly small, but they result from some of the most violent events in the known universe. So things like binary neutron stars merging and smashing together and creating massive supernovae explosions, binary black holes many times the mass of the sun, many billions of light years away, merging at over half the speed of light, and even ripples from the Big Bang itself. And the thing is, if we can actually detect these signals, you can then actually do a whole new form of astronomy, which through a new medium that doesn't use light. So that opens the door for new ways of looking at the universe, which is very, very exciting. And we detect them using things known as essentially we're scaled up Michelson-Morley interferometers. But for our purposes, you can think of them as incredibly sensitive rulers. And when a gravitational wave hits one of these, we try and use these to actually sort of detect the stretching and bending and squeezing of space-time. However, it's quite small. I mean, this is stretching and squeezing on the order of like 1/10,000th diameter proton. So it's very, very, very hard to do this. And not only is it important that we detect these things, but once we detect them, we want to actually sort of extract some interesting information about the signal. So we do that using Bayesian inference. So we use it to extract things like, the masses of the systems, how far away were they? And as I'm showing here, we try and produce sky plots to predict sort of where they came from in the sky, which we then alert other astronomical partners, other telescopes, for where to point their telescopes in the sky. So we can then do follow-up analyses. However, this is like a very computationally expensive process to do using Bayesian inference. It can take of order hours to days to weeks, which is a long time to wait. So we thought, is there a way that you can actually speed this up, perhaps using a form of machine learning? And it turns out you can. So in our case, for this study, we ended up using a form of conditional variational autoencoders, but in fact, we start from first principles where essentially what we do is we start our derivation from defining a cross entropy, trying to minimize cross entropy or the difference between the true, essentially Bayesian posterior, and whatever we're trying to get to approximate that, which in this case is going to be our neural network or model. We do a bunch of math, which I won't show here, and then we end up with essentially a cost function at the end, which describes many of the constituent components of our model, which sort of kind of fall out of it. But at the poster, I can describe some of these details. I'm describe more of this in more detail later. But essentially, that's our scheme. And we train this on a bunch of binary black hole waveforms buried in noise, and we try and get it to infer some of the parameters, the source parameters, things like masses, distance, and where they came from the sky, and trying to get to infer sort of posteriors for each one of these things. And it turns out, when you go to the results, that we can actually sort of match standard benchmark analyses used currently by LIGO, standard Bayesian inference analyses used by LIGO. So our results are actually, this is for one test case, so one gravitational wave waveform. But we do this for multiple to ensure consistency. But as you can see here in this plot, we're trying to predict 7 different parameters which describe the signal, including importantly the sky, where it came from the sky. And you can see that we're generally consistent with every other approach, which is very, very exciting the first time that we saw this. And importantly, we also get about a 6 order of magnitude, 6-7 order of magnitude speed up in performance. So if we go from this taking hours to days to weeks to do to, down to less than a second, which will hopefully have big implications going forward for how we do our primary estimation analyses in the collaboration. But if that piques your interest, feel free to stop by my poster and the GatherTown session later on, and we can discuss further. So thank you very much.